Hello everybody, this is Gordon. We're back for another set of problems. This is going to be Intro to Vectors Set 2. And as before, vectors, we have the relationships where the resultant vector is the sum of the two vectors that make it up. To find the resultant, you add all the x components together and you add all the y components together, making sure that you keep direction orientation preserved. The magnitude of the resultant is the square, the sum of the squares, the Pythagorean theorem. And here we see how to break down a vector into its components, where we have vector in the y direction r sine theta, vector in the x direction r cosine theta. Our first problem, a man walks eastward 5 miles, then northward 10 miles. We're asked how far did he go and in what direction could he have headed to walk directly there. So we have vector A as 5 miles east, vector B 10 miles north. And just to diagram that out, Cartesian coordinates with x and y axes, A being 5 and B being 10. And what we're asked to find is the resultant vector that joins the two together. How far could he have gone? Well, the magnitude of that vector is going to be the square root of the sum of the squares. So it's going to be the square root of 5 squared plus 10 squared, or the square root of 125, which is equal to 11.2. And this will be, of course, distance 11.2 miles. What direction could he have headed to walk there? We have a number of different trigonometric relationships we can use here. We have cosine, sine, and tangent. Since we know all three lengths of this right triangle, we can use any one of those. We use cosine. Cosine is the adjacent over the hypotenuse, in this case 10 divided by 2. So theta, the angle, is the inverse cosine of 10 divided by 11.2, and that is equal to 26.7 degrees. And that's the end of the first problem. Our second problem, an airplane travels 200 miles due west, then 150 miles 60 degrees north of west. We're asked to find out how far did it fly. And diagram this out. We have a westward vector representing 200 miles, and then 60 degrees north of that, a vector 150 miles. We can break that down into its components and find that in the x direction we have a length that is equal to 150 times the cosine of 60. In the y direction, that vector length is 150 times the sine of 60. And so summing up the x components and the y components, we have a 200 miles plus 150 cosine 60, which is going to equal 275 miles. And then b 150 times sine 60, or 130 miles. The vector that we're looking for is the one that joins A and B together. We'll call that r, and the magnitude of r will be a squared plus b squared as before. And so substituting in values, we have 275 squared plus 130 squared. The numerical value for that is 304.1 miles. The third problem, a boat headed north at 8 kilometers per hour experiences a wind pressure causing a sideways motion at 2 kilometers per hour. A tidal current is present flowing 30 degrees south of east at 5 kilometers per hour, and we're asked to find the boat's velocity. Always, always draw pictures and understand what it is that you're looking at. We'll use north as a positive direction, so A will be 8 kilometers per hour north. We'll use westward as a negative direction, so that should be negative 2 kilometers per hour west. And then we have the other vector, which represents 5 kilometers per hour 30 degrees south of east. We'll break that down into components as we do. So C in the x direction will be filling in the c is 5 kilometers per hour, and the theta, of course, 30 degrees. So c in the x direction will be 5 times cosine of 30, and c in the y direction will be 5 times the sine of 30. And so we can sum all these vectors up, all the vectors in the x direction and all the vectors in the y direction. So we have r sub x, or r in the x direction, is going to be b plus c in the x direction. B again, -2, since we're doing west is negative and east is a positive direction. So -2 plus 5 cosine 30, that is equal to 2.33, and the answer is going to be in kilometers per hour, since that's the units we've used throughout. And the direction, of course, to make it a vector, r sub y, or r in the y direction, will be a plus cy, or c in the y direction, which is 8 minus 5 times the sine of 30. And when we punch the numbers in the calculator, we come up with a numerical value of 5.5 kilometers per hour. And so to determine the boat's velocity, we need the magnitude of that vector. So it's going to be, once again, the square root of the sum of the squares of the components, or 2.33 squared plus 5.5 squared. We do that, take the square root, we end up with 6.0 kilometers per hour. The fourth question, we're asked to find the minimum force parallel to a ramp, which will draw a machine a weight 900 newtons up a smooth ramp. The ramp is 6 meters long. The platform that it goes to is 1.5 meters high. Draw the picture. You have a ramp 6 meters long. It goes to a platform 1.5 meters high. The angle that it makes with the ground, theta, we need to find. We don't know. And we know that the weight of the machine is 900 newtons. We break that down into components as we had before, one that's parallel to the ramp, and we'll call that F1, and one that's perpendicular to the ramp, and we'll call it F2. What we want to find is we want to find a vector r that's equal to the negative of F1. That'll be the minimum force required to draw the machine up the ramp. F1 is going to be 900 newtons times the sine of theta. We don't know what theta is, but we don't have to know what theta is, because we know what the adjacent side of the triangle is and what the hypotenuse of the triangle is. The adjacent is 1.5 meters. The hypotenuse is 6 meters. And so the sine of theta is 1.5 divided by 6. So the force, which is going to be opposite F1, is 900 newtons times the sine of theta, which is 1.5 over 6. And that is equal to 225 newtons. Our last question, a great question. This is actually an experiment or a deduction that was done by a gentleman named Bradley in the 1780s, I believe. A telescope has to be inclined 20.5 seconds of arc with the vertical to see a fixed star directly overhead. Earth's orbital motion gives the telescope a speed of 18.5 miles per second at right angles to the direction of the star, and we're asked to deduce the speed of light. Drawing the picture, we have the speed of light coming straight down to the ground and the telescope moving perpendicular to it at 18.5 miles per second, and A, the resultant vector, the apparent direction of light. Theta is in seconds, so we'll have to convert that to degrees so that we can take the tangent of that, or the sine, or the cosine for that matter. From the relationship, we have tangent of theta is equal to the velocity of the telescope divided by the speed of light. We manipulate that so that we have the speed of light is equal to the velocity of the telescope divided by the tangent of theta, which is the tangent of 20.5 divided by 3600, which is the number we use to get it into degrees. We punch numbers into the calculator. We come up with a value for the speed of light, 186,141 miles per second, which if you convert to meters per second, comes out pretty good. And that's the end of the set. Thank you very much.